Uh, Hello all. In the earlier lecture, we have seen the characteristics of a solar cell, in particular the IV and PV characteristics. So with respect to the, and we have seen how to plot the maximum power point with respect to current and voltage. In this uh, video, so we'll just see how to increase the voltage and current in an array of a solar panel. And what is the importance of, or what is the significance of this current and voltage in a solar panel? See, mainly we work with the uh, automobile, so or any electrical vehicle. So if you want to power with solar panel, the voltage and current required is much higher. So increment in decimal values is no longer uh, saves. So we want to multiply in terms of 10 and 20s, right? Now, how to get such higher voltage? So that can be achieved in two ways. So one way is by connecting cells in series, and the another way is in parallel. See, we'll see how to increase the voltage. So this is a typical cell, a series connection of with four cells. So where the positive terminal of first cell is connected to the negative terminal of second cell. Likewise, the positive terminal of negative second cell is connected to the negative terminal of the third cell, and so on. So and this from this connection, the total voltage which we get is 76 voltage, and the total current is 8 ampere. So if you just multiply these two, we'll get the total power. Now, the thing in this series connection is whatever the current generated in this connection will be same throughout the circuit. So there will be no change in the current value. But in the case of voltage, see, if you just measure the uh, voltage across this cell alone with the help of voltmeter, you'll get 19 volts. And similarly, second cell it get divided, and third cell it get divided by 3, and it fourth cell it get by 4. So the observation is there is no change in current value, but the voltage gets divided across all the cells. So we'll take the advantage of division of voltage in from this series connection. So from this, we what we understood is, so if cells to be connected in a series, we will be able to increase the voltage. Now, how to increase the current? So in see, all the negative terminals of all the cells are connected to a single line, and all the positive terminals of the cells are connected to a single line. And the total voltage obtained is 17 voltage, but the total current obtained is 32 ampere. See, if you just take any voltmeter and ammeter, you measure the current across the cell, it would be 17 volts per 8 ampere. Okay, so this is how we multiply the current in uh, this parallel connection. So, so from this, we can tell that the cells to be connected in a parallel, then we can able to increase the current. So with this basic, we'll move to the forward. Now we have seen earlier we have seen the individual characteristics of IV and PV characteristics with respect to only a single cell. Now we are going to see how to increase the IV characteristics of an array. Now, what is an array? So an array is nothing but the two or more cells which are connected in a series and parallel connection, or all the cells which are connected in series and parallel or combined together is called an array. And another term which we call in array is string. The string is nothing but so connecting two or more cells in a series connection. We call it as a string. So these are connected in a series. So we call it as a string one. So this is string two. This is a string three. And overall, we can call it as three strings are connected to a parallel connection. So like we can call it as. So this is how a solar panel looks like. So with the combination of many solar cells, right? Now this is okay. Now how we can tell that so these many number of cells required for my uh, product, or if I have any a small electrical vehicle which I want to run with an solar power, so much of so many cells are required in a panel, or the output of panel should be so much of watts. Now how to design that? So that is what we are going to see the further. So I have taken a typical example from the textbook, so which I will share with you. So with this example, just we can come to know how to design uh, an array, or how many cells are required for a panel. Okay. See, there is a small electrical vehicle, so and there is a small motor, so which runs with the DC current, and that car specifications are required to run is 1.5 voltage at zero point 0.3 amperes, and the car moves at 1.0 meter per second across a high school gym floor. So this is what mentioned here. And the irradiance on the gym floor is given 300 watt per meter square. And the solar cell which used in this vehicle is silicon, and the area is 15 centimeter square. And now I want to design a array so which meets this specification. Know how to design that. So first we want to calculate that how much amount of short circuit current is generated from the or produced from the a single cell. Okay, so that is what is zero point 0.3 ampere is the requirement, and the irradiance is 300 watt per meter square, and the area is 15 centimeter square. So if you just convert all into a single unit system, and if you multiply this, we'll get 0.135 ampere. This is only from the a single cell. Okay. And now the number of branches. So we know from a single cell. So this, if you consider this an array, so this single cell will produce 0.135 ampere of current from this cell. Now, how much amount of current produced in this cell will be the same amount of current in this string. So there will be no change in the current in the string. If I want to produce the current, whatever that will be, that has to be higher than the mentioned. Okay, because this 0.135 only I got, so it is not enough because the required current to drive this motor is 0.3 ampere, but which I got is 0.135, right? Now the required voltage is also 1.5, but a typical silicon solar cell will have earlier we have seen it is like 0.5 to zero point 0.6 voltage nearly. But in general, if you we cannot have uh, as like a solar cell with zero point 0.5 or 1.5, so we have to round up that value. So this 1.5, it will be rounded off to 3 voltage. Okay, now how to get this 0.135 into at 0.3. We have to meet to this 0.3a value. Now this cell produces 0.135 amperes. Now if I multiply with 2, so I'll get roughly 0.27. So which is also less than the 0.3 amperes. Now if we multiply with 3, 0.135 into 3, so it will be 0.405. Okay, so that will be more than the 0.3 ampere. So it will be okay that, so we are crossing the required value. So then the value is like the whole string, so which we want to produce is like 0.3. This the desired value for this string is 0.3 amperes. Now the current which is produced in this cell is 0.135. So if I want to know how many cells in a string to be connected, so just divide the desired output or the required output and then the how much which is generated. Then the value is 2.22. So which I'll round it off to 3. Now the cells in a string means, so this is a string, the number of cells in a string is 3. So 3 cells per string. And also we know voltages, we have rounded off to 3. So voltage will be same for all these 3 strings. Now, so if you multiply 3 into 3, that is 9 cells. So 1, 2, 3, and if you multiply the parallelly, we'll get 9 cells. So this is how we design an array. So that gives the power required for this, or which helps to drive this electric motor with that speed. So we have seen only this is a rough design. So there are some values are higher and lower. So where we have to compensate with the help of some resistance to incorporate in the model. So which we have not done yet. Yes. So we'll understand how to do the way of. So earlier we were seeing a rough calculation and rough design. Now we'll see how to meet exactly the required parameters. So to understand that, so we have the IV characteristics for the same example. So whatever the plot is given here, this is taken for the same example for this same problem also. So this is the IV characteristics of the that vehicle which is moving in the gym floor. Okay. So this is the array IV curve, and this is the array power curve. And to compare with this array IV curve, so we have a single cell IV curve. So this is array means, so the cluster of all the cells combined. So like this cell has an IV curve, this cell has an IV characteristics. So each and every cell have their different characteristics. So if you cluster all those things and if you plot a single IV curve for the whole array, so this is what it looks like, and the array power is this. And this only with respect to a single cell in an array. So that's why so the values are much lesser than the array. Now, what to look at in this array characteristics? Now, how to use this plot to get the exact values to drive that electrical vehicle. Now, from this array curves, the current produces 0.45 amperes. Actually, the current produced per cell is 0.135 ampere. So there are 3 cells in a string. So 3 into 0.135, which gives 0.45. So that is plotted here. Okay, 0.45 is much higher. So if you just extend this curve, will go above 0.4. And the open circuit voltage measured is 1.7. So this will fall between 1.7 and 1.8 exactly here. Now, another thing is the array's maximum power point. These are the, with respect to the open circuit, like this is the short circuit current, and this is the open circuit voltage. But the maximum power point will differ from the other two values which I have talked earlier. Okay, because that those with respect to the area under the curve, right? And now, if you plot, if you multiply the values, we'll get the power value higher. So if you just plot against the maximum power, so if you just cut this graph, you'll get maximum power point values as maximum voltage is 1.46. So this is the VM, and the corresponding current is 0.39 ampere. So this is just below the 0.4. So here the IM and VM values. But if you look at the motor operating conditions are given is 0.3 amperes and 1.5 voltage. So these are the required or the desired values which we want to achieve from the array, right? Now, yeah, so this is the desired value is 0.3, and so this is the desired value. So if you just extend this 0.3 value onto this curve, which exactly cuts here, and if you just bring, if you just extend the line to the downwards or on the voltage, you'll get the voltage value. Okay. Now for this 0.3 value, the required value is 1.6. Okay, but the array's value which we got is 1.7. Yes, the desired motor operating point at 3 ampere is 1.6, so above 1.6. But what from the from our calculations which we got is, so 1.46, and the current value is only 0.39. Okay, now there is a difference, like the whatever the value which we calculated from the theoretical, so which is not matching with the, or which is not falling under the curve of IV characteristics. So there is a difference here. Now, how to meet that difference? That is, so there is always the right? Yes. 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 See, at this, the array produces about only 1.6. Okay, but not 1.5 and not 1.5 voltage and 0.3 amperes. So there is excess of voltages there. Now, for that, if you calculate the power value for this values, and the load resistance is 5.3 0.33 ohms to deliver 0.3 ampere current for this motor. Now, if there is no action were taken, the model speed would change until the motor's operating point lay on the array's IV curve. So it means that the speed of the car will try to get increased. But for us, the desired speed is only 1 meter per second. Okay. Now, how to minimize the value? Because the maximum, the resistance which we can provide with this motor specification is 5 ohms. So there is extra 0.33 ohm need to be compensated. So what we have to do is, if you just minus like 5.33 minus 5 ohms, so we have 0.33 resistance ohms resistance values extra is there. Now what we have to do is we have to put some equivalent resistance, okay, which is equivalent to 0.33 ohms. So if you place any resistor which has 0.33 ohms value, then we can able to get the desired speed of 1.0 meter per second. Okay. Now, if I want to have this extra resistance, okay, so there may be like changes might happen in this solar panel cell design. Okay, so okay, yeah. So this is the what we from the theoretical value which we got is 3 by 3. Now the extra 0.33 ohms, so we have to add in this. So where we need to have some extra fittings in this cells, so which would cost extra cells also. So that extra cell is also a costlier. So we won't get a good performance car like solar power car with a lesser like price. So this is how we need to uh, design the solar array. Okay, so whatever like the calculated value should fall within this IV curve. Then with the help of the external resistors to compensate the what the voltage or any other current values. Okay, so with this we'll stop here, and in the next class so we'll talk about the this bypass diodes for the solar panel protection. So, thank you.